Antonia Sebastian, or Tony. I'm an assistant professor in the Department of Earth, Marine, and Environmental Sciences, and I'm also joint appointed in E3P. And today I'm going to talk to you a little bit about mapping climate risk, mostly as it pertains to flood, but I'll give some nods to some other things that we're working on. And my lab really uses both numerical models and data-driven methods to do this. So if I can figure out how everything works. Despite investments in mitigation, the costs associated with natural hazards are rising. This is just a plot of global damage from all natural disasters across the world. And you can see a general uptick in the costs. And this is a function both of where we're putting people, so we tend to put people in harm's way, but also it's a function of the changing hazards due to climate change and other anthropogenic changes that are happening. Of all disasters, floods are the most frequent and the most expensive, and a large portion of the risks associated with flooding is uninsured. And this is important because insurance tends to be the primary buffer that people have against negative economic or negative consequences of flooding. And it's important to point out that in the last couple of years, global flood losses were estimated to be about $300 billion over a 4 or 5 year period. But they're expected, or they're predicted to reach about $1 trillion annually by 2050. And again, this is a function both of the changing hazards itself, but also largely a function of where we're placing people. And to this point about where we're placing people, in the US, we use something called the floodplain. It's a FEMA designated boundary associated with a 1% chance of flooding in any given year. And this is a planning tool that we use to determine where people build, whether they should be required to have flood insurance to protect their assets, and also drive decisions around infrastructure and sometimes around our natural resources in riverine and coastal areas. But importantly, it's really poorly understood. So I mentioned that it's a 1% chance of flooding in any given year. We call it the 100-year floodplain. Many people think it only floods once every 100 years, but that's really not true. So if you, for example, if you own a mortgage, you actually have a 26% chance of flooding during the life of that mortgage if it's a typical 30-year mortgage. And moreover, not only is it poorly understood, and not only are you at risk if you live in the floodplain, but many people outside of the floodplain are also at risk of flooding. In the US, flood damage frequently occurs outside of these mapped hazard areas. Nationwide, about 28% of insured losses have occurred outside of the floodplain, and 33% of insurance claims, so a third of all claims, have occurred outside of these high hazard zones. And importantly, the rate of this damage outside of the floodplain is growing over time. So on the left-hand side, you see a plot of the fraction of insurance claims that have occurred in high-risk zones relative to moderate or low-risk zones, so red versus green, across the US, but also in coastal counties. And we see that in coastal counties, the fraction of flooding in areas outside of the high-risk zones has been rapidly growing over time. So these lines are in some coastal counties, they even begin to merge or cross, especially in the Gulf and the Atlantic coast. And growing evidence suggests that these uninsured damages have cascading social and economic consequences for things like households, businesses, and communities. My stuff in Google got a little bit weird there. But importantly, exposure to these floods may lead to inequitable social outcomes irrelevant of their financial costs. And so I just quickly pulled two studies here. One looking at educational attainment in this case in Pakistan, and another looking at mortality or morbidity. So thinking back to what Abi talked about, we've seen that the exposure to a flood event has negative social consequences, but especially the exposure to multiple flood events. And so in our lab, we sort of hypothesize that repetitive flood exposure is exacerbating inequalities over time, whether these are financial or social inequalities. In this example, we've mapped sort of thinking a little bit about financial inequalities. Here we have two homes, two households, one that is slightly wealthier prior to a flood event than another. And you can see that as flood events occur, one house recovers faster than the other. And actually, in some cases, one house recovers and the other never does. And so we see that as flood events occur over time, we predict that in places with pre-existing inequalities, their ability to recover or bounce back from these floods generally decreases the more floods that they experienced. But the quantification of these types of risks has been really limited due to a combination of computational costs of, for example, our flood models, and also data availability or data scarcity at these household or these property scales. And so our lack of information about where it's historically flooded in the past, how frequently, and who's exposed to that flooding has led us to hypothesize these things, but not really be able to model them or test them. Instead, we've typically assessed flood exposure to a limited number of extreme weather events, like the largest storm in the record shown here, Hurricane Florence in eastern North Carolina, or a small number of these design storm events like the 100-year flood. And these, while helpful for understanding a single potential exposure to a single event, don't give us a real understanding of this repetitive exposure or this cumulative risk over time problem. And so what does my lab do, or what are we attempting to do at the moment? Our goal is really to advance the understanding of the dynamic interactions between people and the environment and how they're changing over time. Particularly, we're interested in understanding how flood risk has changed in the recent past, so think since 1900, and might change in the near future. So think planning time horizons like 50 or 80 years. And we use a variety of different models to do this, but especially physics-based and statistics-based models. And so I'm just going to provide two examples of some projects we have going on. In one project, this is research that's being led by a PhD student in my lab, Lauren Grimley. We're developing open and replicable physics-based models that are capable of representing multiple flood drivers happening at the coast and how they're changing under present and future conditions. So this, again, here on the left, this is kind of the scale of her model. It spans eastern North and South Carolina. And this is Hurricane Florence, the inundation from Hurricane Florence that she's modeled. And she's also interested in understanding sort of what's contributing to that inundation. And so on the right-hand side, you can kind of see a attribution of different flood drivers, in this case, runoff drivers, so those inland surface waters due to precipitation, and coastal drivers like storm surge. And we're also using this model to start to look at how floods might change in the future and how those drivers might interact differently in the future. So here, this is some model results we got from atmospheric colleagues at NC State, where they model Hurricane Florence and Matthew under 4 degrees of warming, so these synthetic storms in the future. And Lauren's interested in understanding how the relative contributions of those different coastal and runoff drivers might change under the global warming conditions. And here we've seen that, at least for Matthew, the proportion of the flooding that's due to the runoff processes is greatly changing in the future, even if we consider sea level rise. Another project that we have going on is, and this one I'm particularly excited about, is using historical observations of damage together with machine learning to reconstruct flood exposure in eastern North Carolina. And this is work that's being led by Helena Garcia, who's a PhD student, and actually an E3P PhD student. And she's using random forests. And what she's doing is she's generating this really cool database of historical flood exposure in eastern North Carolina. And this is just a map showing the largest 20 events that have occurred since 1996. But hot off the press, she's got a map of 78 events that have occurred since 1996. And we've never seen anything like this with this many events mapped together over such a short time period. And what we're going to use this data to do is really to look at that repeat flood exposure and what happens to societal outcomes. And so a good question in that context is, how are we partnering with other researchers on campus to use this type of flood data, this high resolution flood data for multiple storm events that have occurred in the historical record or might be predicted to occur in the future record, to answer pertinent questions about climate risk. So we're working with researchers, Dr. Greg Trackless at COFIRES, to ask questions around who's holding this risk from repeat flood exposure. We're modeling how these flood events and damages associated with them intersect with things like property values or mortgages to estimate what might happen in the residential housing market as you see repeat floods. We're working with Dr. Pino with some funding from the Coastal Resilience Center to look at how flood mitigation funding flows down to homes and who's getting that relative to who's been exposed repetitively in the past. And through a project with some colleagues at Clemson, we're also looking at how repetitive flood exposure at households and at community scales is influencing educational attainment at K through 12 schools in Eastern North Carolina as people's schooling gets disrupted by floods. And I just wanna, this is where I said I was gonna give a nod to some of the other climate risks. While I'm really, my historical background, my educational background, we're really focused on flooding, we're also starting to think about how floods intersect with other types of climate-related hazards. And in one study that's being led by a PhD student in my lab, we're looking at the intersection between extreme heat and flooding. And this is for Durham County in North Carolina. Where do those two types of hazards intersect? And how do they overlap with different types of social characteristics, like, for example, here, renter-occupied housing. And what you can see on the right-hand side is that as the severity of floods and heats intersecting increases, we also see a larger proportion of housing occupied by renters, which suggests that they might have less capacity to change the structural characteristics of the place that they're renting. For example, adding air conditioning, or let's say, getting funding to elevate their home. So their ability to actually adapt their surroundings to deal with these extreme hazards is less than, for example, in owner-occupied housing. And lastly, the studies that we're working on aren't limited to the lab. I am also just became the director of the Sustainable Triangle Field Site, and this semester students are mapping urban heat islands on campus using these awesome Pocket Lab sensors that we borrowed from the Institute for the Environment. And the goal is really to identify places where there is the potential to maybe mitigate some of these urban heat islands through, for example, thinking about landscape architecture on campus. And so if you want to hear more about this work, I'm plugging it here. They'll be at the Celebration for Undergraduate Research presenting a poster on April 29th, but we're also going to have a final capstone presentation on May 2nd, and feel free to send me an email and I will send you an invite. So that's what I have.